So in this video I have two practice problems that work with manipulating oximes to do, well in this problem, perform a mechanism that gets us from our reactants to our products. So let's just get right into it. Work through a mechanism. I think it ended up being quite long, so don't worry if yours is dragging on, but give it a try and then we'll work on it together. So for this problem, it's kind of important that we have three equivalents of our Grignard reagent. It's going to be doing more than just nucleophilic additions, like in this first step. So in this first step, we can expect that the Grignard reagent will be kind of treat like these, or like there's a lone pair right here. But we know that lone pair is going to come over and pull off the acidic proton. So that's kind of why I left a little bit of space right here so I can show electrons going onto that oxygen. But that'll give us our first intermediate. So now at this point, we can start playing with our third equivalent of Grignard reagent, actually. So let me go ahead and rewrite this Grignard reagent. So here we go. And we kind of pretend like we treat that carbon as if it had its own lone pair of electrons. Let's draw on the proton will deprotonate, because that's what we're going to do now, and start to deprotonate that proton with our Grignard reagent. That'll put the electrons onto this carbon and give us our next intermediate. So with the electrons on that carbon, the next thing to do is to suggest that some of the electrons will flop down and kick out one of the p or pi bonds of the what is almost like an imine. So what I mean by that is to move the electrons down to make a double bond right here. When you do that, you have to kick some electrons off of that carbon onto that nitrogen. Now, you can give nitrogen a negative charge by doing this, or you can give it a neutral charge by kicking out this oxygen with a magnesium bromide attached to it, which is a perfectly fine thing to do in this case. Magnesium bromide works just fine to stabilize oxygen's negative charge when it falls off. So this will bring us to our next intermediate. So now with our two lone pairs of electrons on nitrogen, we can give it its octet by letting these electrons come down to create a double bond. And by doing that, we can push the double bond electrons through this carbon and attacking that nitrogen. So it makes an azirine. And that's what we should expect to see in our next intermediate. So here's our azirine. Just be very clerical. That group, that's our azirine. It's going to be susceptible to our third equivalent of our Grignard reagent, because remember we had three to start with, and so that third one will come into play here. And so I'm actually going to say that the first step will be to introduce that Grignard. Let it come by and attack the azirine. And the second step will be what the second step is always for Grignard reactions, and that'd be to follow it up with acid. So we are given toluene. That was the other reagent that was thrown in with this reaction. So we could just use toluene and let that be our source of proton in this case. But anyways, that will give you when we draw our mechanism actually. So let's draw that real quick. That attacking right there, doing something like that, followed by the proton coming to protonate. That will give you this. So drawn here in green, and this would be our final product. And this matches what we had in the very beginning of the problem. So that was one manipulation of an oxime. Let's go on to a second example. So in this second problem, it's very similar. We're going to have, again, of course, another oxime, and then we're going to be doing something with some ethyl magnesium Grignard. It can also be assumed that this is going to be 3 equivalents. It's going to be just like the last problem, except we have to determine where our azirine is going to be made. Because we have options, right? In the last problem, we only had one acidic proton that was next to that oxime that we could have pulled off. The other one, or the other side, was connected to an aromatic ring and had a double bond that prevented there from being a hydrogen right there. So let's look real quick where our hydrogens could be. So it's reasonable to look. Notice there's a hydrogen right here, and there are 2 hydrogens hanging out right here. But those hydrogens are in a 7-member ring, so it's not very intuitive, at least at first, um, which way those hydrogens are pointed. So it'd help in this case to use a model kit. So let's go ahead and bring out our model kit real quick. So here's our model. We can have our 7-member ring, so 1, 2, 3, 4, 5, 6, and 7. Our oximine is this thing right here. And the only hydrogens that I put on here, by the way, are only 3, and they're the only hydrogens that are adjacent to our oxime. So again, here's the oxime. We have 2 hydrogens right here, and closer to where there's some bridging going on, we have only 1 hydrogen. And so we need to figure out which hydrogen we're going to pull off to allow our azirine to form. So if you go back to the mechanism that we figured out from the last problem, we figured out that that hydrogen that we pulled off with our base, which was just our Grignard, ended up being the position of the carbon that's going to form our azirine. So let's first notice my model kit doesn't actually come with p orbitals, so I had to draw these. But these 2 p orbitals that are going to make up our pi system right here, they're going up and down. So just like that. I have it shaded pink and green, although it doesn't really matter so much. The point is that they're going up and down straight up with these bonds, with these kind of looped bonds that I have right here. So if we imagine, let's go over to this hydrogen. If we pulled off this hydrogen, so it was right here. If you pull off that hydrogen, you're going to have a p orbital that's going to have those lone pair of electrons that are left behind, and they're going to hang out in the same direction that the hydrogen was pointing. So you can kind of tell from the nub it was pointing out this way, and so you can expect your p orbital to be going out that way as well. Well, remembering what our 2 p orbitals that made up our pi system right here looked like, they were going up and down. So we can kind of show it like this. So here they are going up and down. So right now, the way that they're shown, they are perpendicular. So our 2 p orbitals that make up the pi system are perpendicular to the lone pair that exists in a p orbital over here of the hydrogen that we just pulled off. And so there won't be very good stability going on because those two cannot form a p orbital system together. So it does not make the system any more stable pulling off this hydrogen. But if instead we pulled off one of these 2 hydrogens, so one of these 2, we can kind of look at it if we turn the molecule like this. The one that we just pulled off and we talked about was this hydrogen. Well, this hydrogen and this hydrogen are just about doing the same thing. They're both going outwards here. So outwards that way and outward this way. This hydrogen, however, is pointed upwards. And so we can kind of see that if you pulled off this hydrogen, the p orbital would be going in the same direction of it. And it just so happens that it is also the same direction as our 2 p orbitals that make up the pi bond over here with our oxime. So we can kind of show that real quick. So there are the 2 p orbitals. And if you pulled off this hydrogen, there's that p orbital. And so you can see that there's going to be some phase overlap, which is good. They will overlap, they'll be able to interact with each other, and that will overall lower the energy of our molecule. And so lower energy is going to trump high energy all the time. And so if we can have something that's going to be lower energy pulling off this hydrogen, as opposed to pulling off this hydrogen or this hydrogen, it's going to be easier to pull off this one. So that's kind of a molecular orbital idea of why this one's going to be pulled off. And I guess extending that, that means that our azirine will be formed with this carbon and this carbon. So maybe it's easier to see that way. You can kind of see it'll form like this. So let's go onto the board and draw what we just talked about. So after using the model, we determined that we are not pulling off this hydrogen. That's a bad hydrogen pull off. We are pulling off one of the hydrogens over here that are going to line up nicely with our two p orbitals that make up the pi bond. That's going to be one of these hydrogens. So since it's on the board here, it doesn't really matter that we pick which hydrogen it is. We can just say it's the hydrogen that matches up with the orbital. So mechanism-wise, it's going to be the same exact mechanism. And so we don't really need to go through the mechanism from the last problem, because we know, if I just paste it real quick, we can pull this over. We know that our azirine is going to be formed not near the bridgehead carbon. So we don't want to form anything over there. It's going to be formed away from that. So let's draw our nitrogen bonded like this. And here is that ethyl group that'll be bonded to it in the end.